Hello and welcome back to Calculus 2, section 7.9, differential equations. Definition, right off the bat. Differential equation is an equation which contains independent variable, function, and its derivatives. Mathematically, we write this capital F, x, f of x, f prime of x, f double prime of x equal to 0. You understand this notation from Calculus 3 as a function of multiple variables, where each one of these variables in this case is a function. The next major concept after the definition is that the solution of differential equation is a function. You can say y equals f of x. And that's the same one that it's plugged into the equation itself. And then there are many classifications and other things that we will touch upon just a little bit. I want to show probably one of the easiest differential equations that you can think of. Well, the easiest differential equation that you can think of. And that is dy dx equal to 0. Yeah, it's an equation. And if you think about it, right, the way to solve this would be to ship dx to the other side and then integrate both sides. What you get from here is that y is equal to some constant c. Remember that plus c that you put in? And now that makes sense because c is a constant, and if you try to check this work, you will differentiate c and you will get 0, which is exactly what you're supposed to get. You can take a look at a slightly spicier case. dy dx is equal to x. So now you do the same thing. You move dx to the other side, and then you integrate both sides. So what you get now is that y is equal to x squared over 2 plus c. And this is known as a solution. Right? So as you can see here, I'll write it in blood again, solution is a function. Every single equation that you solved up to this section in your math career was an equation. All of them had either no solution or they had a number as the answer. Quadratic equation give you two numbers, like 2 and 5. And then you have trigonometric equation that gives you pi over 4 and 3 pi over 4, for instance. So you solve these equations, but you always get a number as the answer. And now we are going a whole universe up. The answers to differential equations are functions. Now, you can imagine how important this is if I tell you that all of the physics and engineering and technically everything else we know has roots in differential equations. Differential equations are extremely powerful because they can be used to set up a problem which contains rates of change. And we like to measure systems that change. It's not interesting to measure something that never changes, because you measure it once and that's the end of the story. But if you have an evolving system in time, whether it's talk about population or you're talking about whatever, money growth in the account, metabolizing medication in bloodstream, or various engineering things, anytime the system changes or evolves, we can use differential equation to set up the equation, and then we can solve it. Now, what you get on the other end are formulas that you have been seeing in physics and chemistry and economics, pre-calculus courses. Every equation that you used so far is derived using differential equation. And differential equation is so powerful. Let me give you a quick example. So what I'm going to do is I'm going to write a sentence in English. Then we are going to translate that to sentence to math equation, which is the math language, math sentence. And then we're going to use this idea we used up there called separation of variables to solve the problem. So you say, the change of population in time it's important to fit in one line. The change of population in time is proportional to population. It's important to fit everything in one line. So there you go. Yeah, I'll fix it. What happened? You're wondering what this is? Yeah. After I wrote this sentence? Oh, yeah. It's a target. Yeah. We have to practice. Now I want to place one more X. No. So what we have here is a sentence which makes sense in a world we live in. If you look at this sentence, it says that the population is going to change in time. How does that happen? Well, the new units are born and the old one are dying or are eaten or whatever. So you can talk about whatever population you want. There's always going to be some type of a birth, and there's going to be some type of death. Whether it's old age or being eaten, it doesn't matter. Or whatever else you can come up with. Some people text and then they expire. So what we do is we translate this sentence to mathematical sentence. The change of population in time is the rate, which we generally write as a derivative. So change of population in time. The word is translated as equal sign. The word proportional is k times. It's a constant of proportionality. So k, and then you have population p. And there you go. Well, p of t, but population in time. But it's just p as a number now. We know it's population in terms of time because we are differentiated in respect to time. And there it is. In all its glory. You take a sentence. You take a sentence and you write it as a differential equation. And now this differential equation can be solved the same way we solved the equations above. If I say dp dt is equal to kp, I can use the method, the easiest and cheapest method of differential equations called separation of variables. What we do is we put all of the variables of one kind on one side of the equation, all of the variables of the other kind on the other side, and constants can go anywhere. So I'm going to leave k where it is. I'm going to bring p to the left and dt to the right, because dp and p are both population. One is a change in population, the other one's population, so that's all population. It all goes on a pile. And on the other side, I will just have k dt. From the pen.
Oh, the dp.
This one?
No, where's the d coming from? kdt.
It's dt. I'm move it as a differential. Oh, good?
Yep.
Good. When I integrate, what do I get when I integrate dp over p? ln of absolute p. Exactly. On the other side, I have kt plus c as a constant. Now, so far, you know, in mathematics, you Calculus 1, Chapter 5, Calculus 2, Chapter 6 and 7, you deal with integration, and when you forget plus c, what happens on the exam? Take a point off, right? But you still have your 9 points. And it's still A, even though you forgot plus c. You know what happens when you forget plus c in differential equations? Minus 5 or minus 7 or minus, yeah. Just for forgetting one thing. Because that grows into a lot of stuff in differential equations. You forget this thing in differential equations, your problem is most likely over. And there's no way at a passing grade in that class if you are forgetting plus c in every. It is not going to be, I mean, it's going to be important here as well, but you know, when you take differential equation class, it becomes obvious very quickly within first quarter of a chapter 1 that forgetting plus c is just our question. We are going to e both sides to get p alone, and now I'm going to write it as a p of t, right? Because it's a population in time. Yeah, it changes in time. On the other side, you have e to the kt plus c. And if you recall your algebra at all, a to the m times a to the n is a to the m plus n. So these two can be split into e to the kt times e to the c. And I'm going to call this constant a. Sorry, I'll call it P0, what it's supposed to be. So population in time is equal to P0, P0, P initial, whatever you want to call it, e to the kt. Oh, you know this equation from your PreCalc, right? You know this equation from your chapter 6, 6.8 or 6.9, 6.9 when we did population and stuff. See, this equation came from a sentence, a word problem that was considered, and since the words that were used were change of population in time, you write it as a derivative and it creates differential equation. As soon as you have derivative in the equation of any kind, first, second, third, 17th derivative, it's differential equation. So we start with a sentence, we write the differential equation, which is called modeling, when you take what you observe in nature and you write mathematical equation on it, and then you use whatever method is available. In this case, separation of variables worked. You go down this calculation and you obtain something that we call mathematical model for population. And now you analyze this model and see if it's viable. You take a look if this model makes sense. You take the limit as time goes to infinity to see if it's going to accurately show, the future, and so on. Yes?
C can be like any constant. How do you know that e to the c is P0?
Very good question. So the next question is, how do I know that e to the c is P0? I actually don't when I'm writing this. You saw me, I wanted to put a, and I said, let's put P0 right away. And now to show that this e to the c is actually P0, we can, on the side over here, let's do it, I don't know, green. So if you have that the population in time is equal to this unknown e to the c, which I called P0, and then e to the kt. What happens at the beginning of time when you start measuring something? T equals 0. So we are going to plug in over here t equals 0. What happens at that point? When you plug t equals 0, so this is initial population P0, because at t equals 0, you have your starting population. And then you realize that P0 is equal to e to the c times, right, e to the 0 is 1. So you see from here that P0 is e to the c, which I didn't define as, right? So now, to understand the answer, this is population at time t. 1 year, 100 years, 3 minutes for bacteria, whatever. This is initial population. And you have time, which could be in years or minutes or whatever. And then you have this proportionality constant k. Now, if you really think about this, you see this model is capturing the essence of population change. It's not perfect, we'll see that, but it has the necessary ingredients. You start with initial population, you have the time to pass, And with this k, everything will change into a population at time t, which is the t from the exponent. So at least, mathematically it checks out. And then you think deeper about this constant k. Does it make sense, right, to have that constant k, and what does that constant represent in a physical reality? So say we start with a population initial population P0 equals to 500. Pick whatever, 500. People, monkeys, ants, I don't care. Right? Well, I should care. Because of biology. Now, we have initial population. That initial population has its qualities. So in the equation, that population at any time t is 500 e to the kt. I want to know, what do you think k is supposed to be if this is, let's say, 500 female rabbits, initial population? What's k?
Is the husband present?
I said initial population is 500. The universe contains 500 and they're all female. Uh-huh. Why is k 0? Exactly. 500 female rabbits, that's the population. The population cannot change with a positive k because the population would increase. You have to have, as you said, husband, you have to have a male rabbit, at least one, but we chose all 500 to be female. This population cannot change upward with this, so k equals 0 is just fine. Now you can replace those 500 female rabbits with 500 male rabbits, and that same thing happens. So you see, this k would capture something like that. And now you're going to toss in that concept. I will fix this, the initial population of 500 immortal female rabbits. And the problem is fixed. Because the death is a more complicated problem, straying away from this model. Because we are going to subtract the delta t, which is the death function, and then plus beta t, which is the birth function. And then you have predator-prey models, and you have to build upon it over and over and over again, and it's going to be one of the sections in your differential equations, should you choose to take that course in the future. So this k, for now, is very crude and rudimentary, but it does the trick. If I have 500 of whatever of the sexes, unless you're in California, then it becomes different. But anywhere else, you pick 500 of whatever, and it's clearly k0, because population doesn't change. And remember, these are immortal, so we're not going to talk about death or them being eaten or not having enough cabbage. Yes? There is time change, but k being 0, you can wait 5,000 years. It doesn't matter. Population of rabbits cannot change because k is 0. In order to make new rabbits, you have to have male and a female rabbit, right? If it's 500 either male or just 500 female, it doesn't matter, right? That k has to be 0 because time will go on, right? And many would say, well, you need negative k because rabbits will be dying. Sure, rabbits will be dying, but now let's just put k equals 0 and say these are immortal rabbits. So with this type of equation, 500, now k is the factor. Now, in the environment, we can count the population and then wait some time, maybe 2 years, and then go and count the population of rabbits again. That would give us a point of reference in time, which would help us figure out k. When we have, obviously, mixture of male and female rabbits, when there is a habitat there with the food, when there are the predators and all of these kind of things. Now, each one of these factors should add its own part to the equation, but in the most rudimentary equation that we have over here, all of that is mushed together in k. But then again, this is not the best model that we can think of, because having the model that population in time is equal to initial population times e to the kt, if you do the limit of p initial e to the kt, where t goes to infinity, and where k is obviously positive, so the population increases, you get infinity back. And we see that that's a big issue, right? Because you don't have an infinite space, infinite resources in terms of food and everything else to keep these rabbits multiplying all the way to infinity. So on the graph, the initial population P0 is at the y-axis, so that will be, in our case, our 500. And then you can see that as t goes to infinity, population shoots to infinity. So this would tell us that this model is not good for long term, because, again, we cannot have infinite amount of rabbits or whatever else on the finite surface, which is the planet, habitat, or whatever it is. Yes?
Two burning questions to ask since you started the lecture. And when you first talked about the differential equations, this brought me back to solving systems of equations back in algebra and PreCalc. Would you say it's kind of the same thing? Instead of getting intersection points, we're getting intersection curves?
That's going to be when we actually solve systems of differential equations. So you would be, yes. So you will be solving multiple equations. You will be getting multiple answers as functions. So these equations are single equations where you get one or two functions as the answer. But we are also going to have systems of differential equations. And then linear, nonlinear, we call them dynamical systems. So there are courses devoted to that in the graduate school for that. So that's going to be down the line. And what else? You said two questions.
Yes. The other one, well, if they were somewhat similar, and the solution for system of equations is just points, graphically, on XYZ plane, what would the solution look like? What we're talking about?
Well, I'm going to show now another way to solve differential equations, so you will see graphically. We're talking about slope fields, but you can, you are still confined to two dimensions. Is just the nature of the solution could be a wave or could be a function, and then where's my differential equations? There we go. So if you go here to look at the forced oscillation, so if you look at this solution, right, you see three waves on a pile. There is a wave that has a 2t, 7t, and then 1t. So all those waves are added together to create one wave that propagates through, but it actually contains of these three waves. And these three waves, each one has its own amplitude and orientation with positive and negative, so on. So this is what happens in differential equations. You get these multiple functions that stack together and do things. So you're not adding dimensions. You are building functions in a different way that you used to. So you'll see where that leads as you keep taking courses. So, good. All right. So these are the concepts that are the most important. Now we observe something in the nature, and once we observe that thing in the nature, we write English sentence first, and then we translate that into mathematical sentence, and it turns out to be differential equation if it has the derivatives, easy. And then after that, we solve the differential equation, and then whatever equation we get at the end is the model for the situation. We can analyze that model and see how good that model is, how well it predicts the future, because we have data points that we can use to show. And that's how science is done. All of it, actually. You observe something, you write mathematical equations, solve the equation, you look at the model, and you see, you make a prediction, and you go and do the experiment, you make sure it matches, and on and on and on and on and on. Yes?
So, kind of side note, but with starting with writing the equation in English, or like writing a
English sentence.
idea in English sentence, does that need more complicated languages to be able to develop more complicated?
No, because they all observe the same phenomena. When you observe the phenomena, which is the population changes in time, and it's dependent on how many, right? Because if you have, think about this. Let's say you have two populations, you have two islands, right? That have same conditions, everything is the same on both islands, and on one island you drop 500 rabbits with combination of male and female. On the other one, you drop 500 rabbits with a different combination of male and female. They have to come up with a different population, right? Yeah. Now, the trick is that a different combination of male and female will yield different rate of birth of new rabbits. And that is going to be captured with K. But then you can take one island and you drop 500 rabbits, and you take another island and you drop 10 rabbits. Right? If you drop down 10 rabbits, let's say 5 and 5, right? And then you drop on another one 500, which is 250 and 250, let's say. Right? The population with 500 rabbits, starting with 500 rabbits, is going to grow much faster than the one where you start with 10. So the constant of proportionality, when we say the change of population in time is proportional to the initial, right, the amount of rabbits, to the population, sorry, not. You drop down 500, you drop down 10. So clearly they're going to grow differently because you dropped, 50 times more on one island. Yeah. But then the word proportional is the ratio between male and female, which is that K, because you know that K eventually ended up in the exponent. And that one was taking care of the ratios and so on. So if you drop 500 rabbits on one and so female, that population will never grow. And you drop 10 rabbits on the other one, half and half, let's say, that one is going to grow. And it's all about this K. Now K you calculate through the additional point. So this is what we have in terms of differential equations. You read the words, and then you translate those words into mathematical sentence. You solve that because it's going to be a differential equation. Now, with classification, we are going to say that if the equation contains the first derivative only and no higher order derivatives, then we say that's a first order differential equation. If the largest order is second derivative, then it's a second order, third derivative is third order, and so on. So we will say that the highest order derivative equals order of ODE, ordinary differential equation. I'm sorry? Differential equation. or the ordinary concept we're talking about tonight. So now, the equation which we just solved is the first order differential equation because it only contained the first derivative. We can have second derivative, third, fourth, and so on. I've never seen differential equations using more than 4 derivatives in application, but for the sake of math, it can go to any order, because you know that you can take 107 derivatives of a function. So the 107th order of differential equation exists. We don't have a purpose for it, but it exists. We can write one. Now, one of the things that I love about differential equation is that you can always check your answer. So much as when you solve, x plus 3 equals to 5, and you subtract 3 on both sides and get x equals to 2. To check that, you take the 2, plug back in the original equation, you get 5. 5 equals 5, check. So you know that you can box your x equals 2 as the answer. Differential equation is equation, which means whatever you get as the answer, plug it back in, and once you grind once you grind through algebra, yes, you will. What's funny? So once you grind through algebra, you will come up with the same mathematical equality. If you don't, your answer is wrong. So if I got over here 7 equals to 5, I know that my equation is wrong. The answer, right? So we had the differential equation dp dt is equal to kp. That was the differential equation, and my solution was p of t, which is just p, is p0 e to the kt. So this means that when I take this and plug it in the original equation, we have to get the equal sign between the left and the right side. Now you look at the differential equation, and sure, it should be clear that this plugs in there. What do I do with this? Well, differentiate p and then plug that in as well. So we find p prime, which is dp dt, by differentiating the answer, and that will be p0 k e to the kt, because when you differentiate e to the kt, k drops down. So now plug this here, plug this here, and you quickly see that these two are equal. You get p0 k e to the kt is equal to k p0 e to the kt. Well, p0k or k p0, it's commutative, it's the same, so we got the equation to check out as we plug in the solution. It's as simple. Sometimes it takes more effort for equations that are longer, and then if you need 2 derivatives, like the poor souls on the Tuesday exam, differential equation, we had a second derivative to check if there were equations, so they had to take 2 derivatives and then plug second derivative, first derivative, original function, and all of that algebra had to grind to get the answer. Now we also know that for regular equations, where answer is a number, we know that certain equations cannot be solved at all algebraically. If you mix polynomial with the transcendental function, you can just cry about it because you can solve it using algebra. So equation, I don't know, e to the 3x equals to x minus 7. It looks so nice, right? So simple. This equation cannot be solved by means of algebra. Because if you try to apply ln to kill e and free that 3x, you bury x minus 7 under ln on the other side, right? So freeing up one side buries the other. And you don't get to have x's available on both sides to combine them into single x and get x equals a number. This equation cannot be solved by algebra. That's end of story. So how do you solve this? Well, graphically. You draw the graph for e to the 3x. You draw the graph for x minus 7, right? And they will intersect somewhere. If they don't intersect, there is no solution. If they intersect, that intersection is the solution. And guess what? That solution has the x-coordinate, and that x-coordinate is the x equals answer that you are looking for. I can give you a very simple example here. Let's go with the x plus 3 equals to 5 from before. So say this cannot be solved. What do? Well, I have two functions. There is a function x plus 3 on the left and a function 5 on the right. And I can graph those functions wherever they intersect. It's going to be a solution. It better intersect at x equals 2, otherwise we just ruined mathematics and we can all go home. So I start by 1, 2, 3, 4. This is 5. And we get the horizontal line at 5. And now x plus 3. 3 is the y-intercept. And then we have to have this 45-degree line. Look at that. Look at that intersection right there. It's 2, 5. And as I said, drop it down to x, 2. So this x equals to 2 is a solution. Every equation under the sun can be solved graphically. You graph what's on the left, you graph what's on the right, and the intersection, if it exists, is a solution. Its x-coordinate is a solution. Now, remember that solution for differential equations is not a number. It's function, which is infinitely many numbers placed together through the function, linked, right? X and y values. So what do we do for differential equations then? Can I solve them graphically? And the answer is yes. We introduced the concept of slope fields. So say you want to examine the solution of the differential equation dy dx is equal to x minus 1. Now we can solve this, right? But I don't want to. I want to use graphical method. The first thing we realize is that this is the first derivative, and the first derivative is related to slope of the tangent line. So let me pick dy dx to be equal to 1. Now this is equivalent of saying that the slope is 1. Slope m is 1. Now we plug that in, the original equation, and what I get is 1 is equal to x minus 1. I didn't take any derivatives from here. And since dy dx is... Oh, the word pick is tripping you. Yeah. When someone says pick a card, what do? Exactly. So at this point, I picked a card, and the card had number 1 on it. So you pick any value you want. We pick number 1, let's say. We'll pick all other values. I mean, not all other values. We'll pick some other values as well. And what I get here is x equals to 2. Now this is the equation, also known as the isocline. Sheesh, what is that? So I'm going to draw the xy coordinate system, and then I'm going to draw very thin this isocline x equals to 2. And what I do is I place slopes 1 along this line. Slopes 1 are these 45-degree little line segments. And later on, we are going to snake the function through those. Now, pick dy dx is equal to 2. That means 2 is equal to x minus 1 and x is equal to 3. Perfect. Here we go again. Now x equals 3. And along that line, we place, so that line is called the isocline. And along the isocline now, I'm going to place the little slopes, but this time the slopes are 2, not 1. So they're not 45 degrees, they're more slanted. So that's calculation number 2. Let's pick pink. There we go. Pick slope to be 0. I mean dy dx. You can pick anything. If you pick dy dx to be 0, then when you substitute, 0 equals x minus 1, x equals to 1. Perfect. We were missing that one. So we put in the isocline, x equals 1, which is the vertical line. And the slopes are equal to 0, which means they're flat. Now I'm going to pick slope to be negative 1. Yeah, just like when you graph for the first time. And remember when you did graphing for the first time in algebra, you were told to calculate y values for x equals -2, -1, 0, 1, and 2, right? Well, now I'm asking you to do the same thing, except it's a little bit more advanced. Where are the cookies? It's good. So we have -1 is equal to x minus 1. So we have x equals 0. X equals 0 is the x, sorry, it's the y-axis. And we are supposed to draw -1 slopes. So there are 45 segments. Look like this. So 45-degree slopes. Oh, x equals 0. All right. So, when we're at it, let's do -2 and then talk about life. So pick m to be -2, then -2 is equal to x minus 1, and then x is equal to -1. So isocline is at x equals -1. What happened? OCD. It's awesome. So we picked -2. So that's going to be more slanted. Yes, in all of my infinite wisdom, I know. There we go. Do you see the flow?
Yeah.
Right there? Do you see that anything entering, let's say, from here, has to go whee?
Whoa.
Do you see that?
Whoa.
Do you see that this what we call slope field? Yeah. Yeah, it gave up on these lines. Do not be alarmed, it's air conditioning.
It's pretty chill also.
What kind of shape? Each one. It's a parabola, right? And you also see that that parabola is centered, right, at 1. All the minimum values are on this isocline x equals to 1. Do we see that? Now, luckily, I picked the equation that we can solve. So we have dy dx is equal to x plus 1, right? Is that true? Ship dx to the other side, what do you get? What happened?
X minus 1, not x plus 1.
That's what I said, please pay attention. As you integrate both sides, using the separation of variables, we get y is equal to x squared over 2 minus x plus c. Oh. Now, if your mind doesn't explode right now, you have no emotion, you should quit whatever you're majoring. Because this is clearly needed for it. So let's, yes.
Is this plus C why we have so many parabolas?
Yeah.
On the axis line? I don't get the negative. Is it negative on that? Or positive? Equals. Okay,
Equals, yeah.
That,
We have an infinite number of parabolas going up and down. We don't know what C is.
Yes. And now you see all of the mathematics converge together in this one simple problem. You already noticed that I can draw infinitely many of these pink lines top of each other everywhere in the space. And I do that because we have plus C. And what the plus C does all the way from pre-calculus, it shifts functions up and down. So you see that if you pick one of these, by changing the value of C from -2 to +100 to -pi, whatever you come up with for that C, that line is just going to go up and down, up and down, up and down. And you have infinitely many of those lines. This is the general solution of the differential equation. So now I claim this as a general solution. Now, can I have something that's called particular? And the answer is yes. If you give me a point in space, only one of these infinitely many lines will go through that point. And that becomes particular solution. So now, say that you, for whatever reason, right, the entire plane, you want the one line that you are interested in, because you observed a phenomena, you want that line to go through 1, 0. To write what we call initial condition, one, 0 means that y of 0, y of 1 is equal to 0. We can plug that in. We can plug that in into our general solution, and we can calculate C. What are the three variables that you have? It's y, x, and c. And I'm giving you x and a y. You're left with 1. And you can compute that c. And because we isolated a single point on the graph, we immediately pin down x and a y. A single c emerges, which is exactly the c that is going to fit that single one out of infinitely many functions that goes through that point and has this form. So now I plug this in. And what I get is 0 is equal to 1 squared over 2 minus 1 plus c, from where c is equal to a half. So now I get to write. What happened?
-1/2.
Positive is
No,
good.
never mind.
I'll leave it positive. So now I will write y is equal, well, I can put y of x if you want to, is 1/2 x squared minus x plus 1/2. And this one, because of the initial condition, is called the particular solution. It is the solution, the one that goes through the given point. So now if I am
The
to,
point on the graph is 1, 0 or 2, 0?
this point is 1, 0. Oh, 2, 0, whatever. I'll move it over. Yeah, you're right. So I'm going to move it over. Thank you. So all others, that's going to be particular. Mm-hmm.
What about the gap between the parabolas? Is it a small gap, or is it just that specific?
There are no gaps
There is no gap. Is it just a representation?
because C belongs to the real numbers. And yep, there are no gaps. So we see that there is a way to solve the first order equations using this method of slope field. The last, well, there are 3 more things I want to do, but the last definition would be the linear first order differential equation. So linear first order differential equation. I have to steal their letters. There we go. So now, what is the linear first order differential equation? So any differential equation that has the form of y prime of, let's say, t or x, whatever, t, is equal to ky plus b. That's the linear first order differential equation, where k and b are numbers. The solution is y of t is equal to ce kt minus b divided by k. So how difficult are these kinds of problems? Well, first of all, observe, guys, that you have your change in population in time, except now instead of p, we're using y. You see that? Everyone sees that? And do you also see this term, which says proportional to population, right? And then you have additional term, say plus birth or something. It's not plus C. This is in a setup. The plus C situation helped us with this one when we're solving. But in the setup of this, so the definition of the first order differential equation is exactly the problem we did earlier with added plus a number. Now that plus number could be additional population, could be something very positive in the environment, right? Because we see it plus b, so it should be increasing the population.
So in that last situation, y was just x. In the last one we did,
Y was dx.
y was x.
No, y is y, x is x.
No, from the very top.
Over here, we had dp dt is equal to kp. Now you replace p with y, so dy dt is ky, and then you add plus b to it. Abundance of food, let's say.
Yeah, I was referring to the last example.
This one.
Yes.
X's are t's, yes. You can have x or t as the input.
Okay.
I'll see you next week. Now, we can... lost my train of thought. Ah, yes. So we can solve this by separation of variables. You see, in differential equations, it's class on procedures more than anything. You have to be extremely good with integration. You remember your trig sub and by parts and everything else. You remember all of those things. But then you also learn and memorize a lot of solutions that you can just write down without actually solving a thing. You see, if I have a differential equation that says 6y prime is equal to 4y minus 9. I recognize the form, but the problem is that y prime, which was single in the equation, it's not single here. I have to get rid of that over 6. I mean times 6. So I will do divided by 6 everywhere to come up with y equals, right? So I divided by 6 everywhere to get 2/3 y minus 3/2, right? 3/2. And now, from here, it's easy to pick that k is 2/3 and b is negative 3/2. And now when you plug all of this in the equation, the solution just emerges. We haven't calculated we haven't done any calculus integration or anything like that. We memorize the form of the solution and just plug the numbers in. So CE, and then it goes KT, but K is 2/3, so 2/3 T, minus, and the minus will give me a plus, and I have BK, so 3/2 divided by 2/3, which is 9/4. And that's the solution. I haven't done any calculus. But you know what? I am going to do calculus now. Because we don't have to memorize these things. We can actually compute them. It's much faster to know and then just write down the solution rather than going through all of the pain of calculating this. But what I can do is I can say I have this 6 dy dt is equal to 4y minus 9. I do separation of variables, and don't worry about the 6 can stay on either side. So 6 dy over 4y minus 9 is equal to dt all alone and said on the right hand side. Integrate both sides. And what do we get? We get 6 ln of 4y minus 9 is equal to t plus c. No. Yes. Yeah, that's it. We can divide 6 to both sides, so ln 4y minus 9 is equal to 1/6 t, and then this 1/6 will be absorbed by the constant. You don't have to write c over 6. You can just write c. It will be absorbed by the constant. Now, e both sides, 4y minus 9 is equal to e to the c, let's say it's a, so a, e, 1 over 6t. I don't like it. We're supposed to get 2/3. Where's the mistake?
You got the integral of 4y minus 9.
Oh, yes, you're right. When you integrate, you have to divide by, because the chain rule. When you integrate, this needs to be over 4. So that's 6 over 4, which is 2/3. And now it matches. Nice. There we go. And now we have that y is equal to a e 2/3 t, and you do plus 9 over 4. See? Same. So you memorize, if you want to, you memorize the solution to the equation and you just plug in the numbers. All you have to plug in are k, b, and k, right? You have a k here and a k here and a b there. You pick up what k and b are from the equation, just plug that in. At best, you have to, I mean at worst, you have to simplify a fraction. That's it. Yes? E to the c. I'm just redefining it as whatever other variable. So your project will be uploaded this week. You can start enjoying that. What my differential equations have as one of their projects is to pick between the rocket propulsion calculations, which is in the textbook, or cooking. Because if you bake at home, you use the oven, and the oven is the Newton's law of cooling, and the Newton's law of cooling follows the same separation of variables kind of thing. You have the temperature of the whatever you're cooking, temperature of the oven, and then the initial temperature. So you have 3 temperatures that you are playing with. There's time and then k. K is the coefficient of the oven, which is related to the type of the oven, size of the oven, all of that kind of stuff, right? And then also the container in which it has more than that attached to it, but it's fine, and it's pretty good actually. I mean, I calculate every time because it's easier. Set timer down to a second, and I'm free to do whatever I want till the timer goes on. I don't have to go and check it and look at it and all of this stuff, because Newton's law of cooling is something that it's been around for a very long time, and it works. So if you do calculations right, you set the timer for the amount of minutes and seconds, you just walk away. When it goes bing, take it out. You can do another calculation on how long you should, if you know the temperature of the room, how long you should wait until it cools down to the consumption temperature. So you can do all of those calculations and plan the meal down to a second so you can efficiently get the people in and get them out so you can play video games.
You can upload that too. You can get like hot tea, and you can write a function at which they would both intersect, where would be the appropriate time to eat and drink. If that's learning yourself.
That would be your project.
I mean, I wouldn't do it, but that's a possibility.
Yeah, it is. In process now. I want to see pictures.
Okay. You didn't post the project yet.
No, it's coming up now. Because we are finally done with chapter 7. We are behind this class. We are moving slowly. I have to pick up the pace. What happened? All right. Practice problems for you to enjoy. And we're done. So use the separation of variables, right? X squared dw dx is equal to square root of w times 3x plus 1. Lou. Ryan, please leave him alone and let him do the problem. Yeah.
You know, there's no fun. I paid $50 an hour to be a tutor.
What happened?
You know, kind of fun stuff.
I'm not close to him.
What? What are you saying? I don't know, it's so cheap.
I would sound to take the muffler off, sell it for gas. Tank of gas. Drive around top, that's it. You hear that? I know, every time, without a fail.
Is that a different? Okay. He drives it all the way to Summerlin too. Across right now, how it is. What did he? He takes a circle. I didn't ask him that. I mean, I didn't do it that way, but I mean, I wouldn't really do it that way. I would have thought it was okay. You bring Twitter over here, and you guys over here, and you watch it. Yeah, even though it's me and the other one, I told Ryan, oh yeah, Ryan said, he didn't put in the 2 drops of methamphetamine in it. So our titration will be different. He did it 3 times. We're on 3 times. I don't have to do 6, right? All right, so
The homework, yes.
I'm just going to do 7.8. Right.
All right, let's take a look at this problem and then disappear into the night, I guess. So, we use separation of variables, which means all w's on one side, on x's on the other. So dw, we have 1 over root w dw is equal to 3x plus 1 over x squared dx. On the left-hand side, we have w to negative 1/2 dw is equal to, when we divide, we get 3 over x plus 1 over x squared dx. And now we integrate. On the left-hand side, when we integrate, we get negative 1/2 plus 1/2, plus 1 is positive 1/2, so w to the 1/2 divided by 1/2, so 2 times. We don't have to put plus c on that side, because we'll put plus c on the other, only one plus c is needed. This is going to be ln, 3 ln of x minus 1 over x. And then we have plus c. Now, yeah, this is x to the minus 2, so you do plus 1, yeah. Have plus c. So now, we're supposed to divide everywhere by 2 and then square both sides. So w, let's write it as the square root of w is equal to, and now divide by 2, so we have 3/2 ln absolute x minus 1 over 2x, and I'm still going to use plus c because this gets absorbed. You don't have to go, you can write c over 2 if you want to. You can just write c. And finally square everything. So w as a function of x is equal to, in parentheses, everything squared, right? So 3/2 ln x minus 1 over 2x plus c, everything squared.
Square root terms didn't matter. Right? Not square root, I'm sorry. The c squared doesn't matter. That's the one, right?
Well, it's c is added. If you want to FOIL this, you will have 9 terms. And yes, you will get c squared. At the end, then doesn't matter.
That's it.
What happened?
That's it.
Are you disappointed?
So if you put the plus c after you did everything else, then you'll be wrong. Because that would be outside the limits.
Yep. He has to be inside.
Okay. So is there a general rule of thumb when you should add the plus c into your equation?
Immediately after you integrate.
As soon as you integrate. Okay.
Yeah. And then whatever is here, you have to deal with that. So as soon as you integrate, that's when the plus c goes in, and then you just move it around. So only if you multiply or divide c by a number, it gets absorbed. Other than that, you have to deal with squaring and everything else.
Okay.
All right, that's it. I will see you all in 2 days.